What's up, everyone? Today we're talking about soccer ball aerodynamics. So click the subscribe button. And the soccer ball aerodynamics is actually a pretty juicy topic. It actually started in about 2006, and you might think with soccer balls, so it's going to be like a sphere aerodynamics. The sphere aerodynamics does play a big part, but there's also quite a lot of different flow features that occur because of the shape of the soccer ball. You have the seams, and then you have the panels, and it's actually quite interesting. So in 2006, the soccer balls went from the traditional pattern where you had the hexagonal shapes stitched to the pentagon shapes and all around, and there were quite a lot of these panels that had to make up an entire soccer ball. Then for the 2006 World Cup in Germany, the Adidas, I think they made the ball called the Teamgeist, and this was a revolutionary ball at the time. It was the idea behind it was to reduce the number of panels on the ball. So instead of having like 20 or 30 of these very small hexagons or pentagons, you only have about, I think, 14 or so they had, something like that, of these much bigger panels to make the ball more spherical. Because with a regular soccer ball, you have all these seams, and depending where you hit the ball, you kick the ball, if you hit a seam, that's going to impart force differently to if you hit it in the center of the panel. So by making the soccer ball more spherical and reducing the number of seams, the idea was that the soccer ball, when you kick it, would behave a lot more repeatable. So that was the idea behind that. Along with that came a lot of challenges aerodynamically. What they were finding was that these soccer balls were moving very strangely in their flight path. Like they'd be going in one direction, and then all of a sudden they'll just drop or go to the side, and it would really fake the goalies out. And there were a lot of goals that were scored that shouldn't have been scored under regular conditions, but because these soccer balls moved so erratically, the goalie didn't know how to react to it. Then in 2010, the Soccer World Cup in South Africa, they tried to remedy this. So what they did was they looked at the soccer balls from the Germany World Cup and the Teamgeist ones, and they thought that because they reduced the number of seams, you make the ball a lot smoother. And because you make it a lot smoother, it means that you're not not sort of tripping the boundary layer. So for those of you who don't know, tripping the boundary layer means that you effectively introduce a lot more turbulence into a very well-behaved boundary layer to then create a very not well-behaved boundary layer. But with that, you get a lot more energy closer to the surface, so the flow is moving quicker, which means that it will stay attached longer over the surface, and you'll get less drag, and it'll stay attached longer. And with the Teamgeist, which was the first ball in 2006 to do there, to reduce the number of panels to make them more spherical, they figured that because you had less seams, you're getting less of this boundary layer tripping going on, which means that the flow over the ball would just start separating very chaotically. So sometimes it would separate on top, sometimes on the bottom, left or right. And this would then create a force, either lift or side force, which would then move the ball erratically and not predictably. And this was the problem. So then in 2010, with the second soccer ball called the Jabulani, they decided to put all these tiny little ridges on there everywhere, all over the ball. And the idea was that by putting these ridges on, you could then make the boundary more turbulent by introducing a lot more disturbances to the flow, and hopefully mixing in higher movement flow from higher up in the boundary layer into the boundary layer closer to the surface, so in the sub-boundary layer, to prevent stall, to delay it. So they did this, and they found that there were some decent effects. We'll go into a paper in a second that had a look at all these different soccer balls. But then since 2010, there's been a lot of different soccer balls. Like there's been like a Evo Power, Merlin, I think Telstar 18th, all these different balls. And there's a new one coming out this year for the FIFA World Cup again in 2022. And the paper that we're going to be looking at is called Effect of Soccer Ball Panels on Aerodynamic Characteristics and Flow in Drag Crisis. And this is an open source, open access paper, the same thing. And you can access it yourself. I'll put the link in the description. And I'll get this up here. So this is okay, I don't care about that. Okay, so this is the paper here. And what they did was they looked into 11 different soccer balls. And I'll go quickly to which page they showed all these soccer balls on. So here you go. So this was the one that I was talking about first. This is the team guys. This was like the very first one to ever have this approach of reducing all these panels from the typical hexagon and pentagon shapes to just a few really strange looking panels. And then all these other soccer balls, they started doing all these different patterns. So the Javelani here was one that I was talking about, where it had all these tiny little like striations, these tiny little ribs on there. It didn't work as well as what they hoped, but it was still not bad. And they went to all these different ones. And so because these are effectively spheres, they do have, as I said earlier, sphere-like characteristics in the aerodynamic flow. One of the major similarities is something called the drag crisis. And for those of you, you've probably heard like this term in a lot of other aerodynamics. So drag crisis, lift crisis, all that sort of kind of thing. In aerodynamics, a crisis effectively just indicates when the force changes dramatically. And it can be an increase or a decrease. So with this particular case, the drag crisis is the point where the drag on the soccer ball dramatically drops. And the reason why that happens is because the flow over the ball transitions from laminar to turbulent. And that's a very key point. The reason why is because when you have a laminar flow, the flow typically doesn't stay attached as long over the ball. And for soccer balls in particular, the flow usually separates at about 90-degree point, so literally halfway over the ball. As soon as you start to have that pressure recovery, it separates. But then when you have the turbulent boundary layer, the flow can stay attached quite a bit longer, and then you get a reduction in drag, mainly due to a reduction in pressure drag. So pressure drag, if you're not familiar, drag is made up of quite a lot of components, like depending on what flow you're looking at and what object you're looking at, there could be all different types of drag. For example, in sonic flow, you have something called wave drag. In subsonic flow, like very subsonic flow, like max 0.1, there's almost no wave drag. It's negligible. So there are different components. And for a soccer ball, you have effectively 3 different components of drag. There's the typical skin friction drag, which everyone knows. There's the pressure drag, which is effectively a pressure differential from the front to the back, which creates an overall force. And then there's effectively a vortex drag. And depending on which field you're in, that can be called induced drag, vortex drag. This drag is just drag that's created, that energy is used to create vorticity. And there is quite a few vortices that come off of the soccer balls. So the drag crisis that occurs for soccer balls, that's mainly due to a massive change in pressure drag. And that occurs because the flow stays attached longer, which means that there's a smaller wake. There's a higher pressure on the back surface for a lot of it. So that equalizes the high pressure on the front surface. And that's why you get a drop in drag. There's not such a big drag difference. And this drag crisis, the region is called the critical region. This is effectively the transition region. And the smaller you can make that region, the quicker the ball will go between either laminar or turbulent flows, and it will react a lot more predictable. So in a turbulent flow, the ball will fly in a very predictable path. So if you kick the ball, if let's say you go out onto a field and you have your friend and he kicks a ball from 30 meters away, as soon as it comes off the boot, you have a pretty good idea of where it's going to land. By about halfway in its flight path, you have a very good idea of where it's going to come. Whereas when you have the laminar flow, and especially with these types of balls, when even at halfway, you see it coming on a certain flight path, but then due to a change in the separation all over the ball, you would then have a new force that could move it in a lot of different directions, and it'll fake you out. Effectively, it's a knuckleball. So with this paper here, they did quite a few things. They looked at PRV, they looked at some flow viz, but the major things that were interesting were the force measurements, and also some measurements of the groove sizes. So one of the major theories that they had for this paper was, well, it's either going to be that the groove length, so how many grooves there are on the soccer ball, or the groove size, so how much volume there is in each groove, is going to change the flow physics. So they looked at both of these and they measured how long the grooves were in total over these balls, and also the groove lengths, the groove volumes. And then what they found, I think it's figure, here we go. So figure 2, this was them measuring the groove volume. So they measured the depth and then the width and also the general profile, and then they could figure out the volume. And then they did all their tests and everything, and it was in the wind tunnels. And I'll skip to some of the results. So this figure here is really the crux of the paper. And what this figure shows is on the x-axis, you have the Reynolds number ranging from 0 to 40,000, or maybe a bit higher. Then the CD, drag coefficient, from 0 to 0.6. Then you have the velocity from 0 to 30 meters per second. And the reason why they have this scale here is because 30 meters per second is effectively the highest velocity that you're really going to be kicking the ball at. So if you, a free kick, and then they found that actually when you kick a free kick, it goes at about 30 meters per second, which is about 110 kilometers an hour. And then that, by the time it gets to the goal, it decelerates to about 15 meters per second. Actually, this Reynolds number, sorry, is 400,000. So it decelerates to 15 meters per second. So in the distance from a free kick, which is like, I think the penalty box is like 20 yards or so. So it's like over 20 yards away. So let's say 25 meters away. In that distance, you go from 30 meters per second to 15 meters per second deceleration. And interestingly enough, a lot of these balls just below that velocity, they start to have this drag crisis that we're talking about, where you have laminar flow, and then you increase the Reynolds number slightly, and then you have this massive drop in the Reynolds number, in the drag, as the Reynolds number increases, and then you have turbulent flow after that. Just quickly, before we go on, this podcast is brought to you by the MSP Hawk. It accurately measures the temperature, barometric pressure, and humidity in your experiments. So you can calculate the density of air very accurately. If you don't have one of these, the density of air changes like 3 to 4% on a regular day. So that means that you're going to have that 3 to 4% error cropping into all of your measurements, including the Reynolds number, including even just the velocity of the wind tunnel. So this gets rid of that. Every aerodynamicist needs one. There's a link in the description, so pick one up. And getting back to this paper here. So the drag crisis is very obvious. Going from laminar to turbulent, the drag drops by like a factor of 2 or 3. And actually the Jabulani is really arguably the worst performing ball, because it has quite a big range of this critical region. So it goes from about 12 meters per second to 17 meters per second. The best ball was this Evo Power one, and that went from the critical region went from 7 meters per second or so to about 9. Which means that when the ball decelerates, because as you kick the ball, it at its maximum velocity, then it has drag acting on the ball, and then it decelerates over the flight path. And then as it hits this 9 meters per second mark, it will decelerate, and then it will very quickly go to laminar flow. So the ball will then act a bit more predictably. Whereas the Jabulani, for example, which is pretty funny because this was the ball that they put these very tiny striations on there, these little ribs all over the ball. It didn't perform nearly as well as some of the other balls. However, this was one of the early attempts, so it is understandable that perhaps it wasn't as good, just the pattern in general. I think from later on, I don't recall any soccer balls having these striations, so I don't think it's very successful. So in this graph, as mentioned, the range that critical region occurs over is very important, but also the onset of it. So the Jabulani, as I mentioned again, it was bad not only because you had this very large critical region area, but it also started from a very high velocity, from like 16 or 17 meters per second, which means that pretty much any kick that you will see on the soccer field is going to have to go through this critical region here, which means that any kick you see, any ball, it's going to have this unpredictable nature to it. Whereas with the Evo Power, for example, a lot of kicks you won't even see the critical region, so it's going to act much more predictably. So for a free kick, for example, when you kick it at 30 meters per second, that's obviously a professional range. An amateur may not be able to get that high, but even still, even at 25 meters per second, if you have a 15 meter per second reduction in velocity over your flight path, you're still not going to be getting to the critical region, which means that the ball is still going to be acting predictably. So that's quite good. Then they came to some conclusions, and the first conclusion, they had two conclusions from this paper, two main ones. They found that as the groove volume decreased, so remember how we mentioned earlier where they measured the volume of the grooves. I'll go back to that figure here. So just to jog your memories, this is the machine they used to scan the ball and figure out what the groove volumes were. They found that as the groove volumes increased, the critical region becomes narrower. So that EVO power, for example, the groove volumes were significantly bigger. So that resulted in a narrower critical region. Then the other conclusion they came up with, which was a little bit surprising, was that in the laminar range, the drag drops with a lower groove volume. So as you reduce the groove volume, the drag reduces. Their theory was that it reduces the skin friction drag, but they weren't too sure about that, and I'm not too sure about that either, if that would be enough to override any gains you would get in the pressure drag, because if you have a bigger groove, that means you're going to be making the flow more turbulent, the boundary layer, which means that the flow will stay more attached as it goes over the ball. So I'm not sure which drag component there was reducing more than the others, or which one was increasing more than the others to make up for that that relationship there. But in the turbulent range, this was an expected result where as the groove volume reduces, the drag increases, and that was expected because, as we mentioned earlier, like if you have a greater volume, it means that you're going to have a lot more turbulence being introduced into the boundary layer, which means the flow is going to stay attached over the ball much longer, reduce the wake size, reduce the pressure drag, which then reduce the overall drag. Because at the end of the day, soccer balls are effectively bluff bodies, and bluff bodies, as a general rule, like I can't actually think of any bluff body at the moment. In fact, I think probably maybe part of the definition is what I'm about to say, which is for any bluff body, the pressure drag accounts for the majority of the drag. It's the skin friction drag usually accounts for 5 to 10%, 20% perhaps. The pressure drag is usually like 50 to 90%, and then you might have a little bit of drag coming from the vortices. And that's mainly because bluff bodies that have big wakes, and that goes hand in hand with pressure drag, so it's effectively the same definition. So that's why in turbulent regimes, when you have greater groove sizes, the volumes, you then will reduce the drag. One thing they found was that the amount of seams on there didn't have that much of an effect. There was a very weak correlation. So that was an interesting conclusion. So that's the end of this podcast. Make sure to like and subscribe. Check out the Atmosphere Hawk. Every aerodynamicist needs one. If you want to improve your experiments, check it out. And that's all I got for you. Peace out.